Hello everyone, welcome to the second tutorial about DeepMIB. DeepMIB is a new tool which we have in microscopy image browser, and this tool can be used to train convolutional neural networks and then use these pre-trained networks to predict new datasets. In the previous tutorial, I showed how we can train 2D UNet and apply it for membrane prediction in electron microscopy dataset. Today I will talk about 3D UNets, and I will show you how we can train 3D UNet and then apply it to light microscopy dataset with multi-color channels. Today I will use the compiled, it's called deployed version of MIB, and with that I'd like to highlight some differences between the MATLAB and the compiled versions. The dataset that we will look today was kindly provided by Ika Heima and Ulla Pirvala from Auditory Physiology Group at the University of Helsinki. They study mouse inner ear, and the dataset that they provide is quite nice because we can use it to segment inner hair cells, which is this lower part of this image, their nuclei, and ribbon synapses, the small dots around here. Let's take a look on the dataset. The dataset that we will use today has two parts. The one block is for training and another block for prediction. If I open the training dataset, we can see that it has two color channels and 70 sections. If I turn on dilute, the red color channel shows us cell outlines, and the blue color channels shows both nuclei and synapses. I made a model for this training with MIB, and here the model has three materials: cells, their nuclei, and synapses. The second material we will use for prediction, so we will train the network, and then we try to, this is the model, we try to predict this data set. So it's slightly bigger, and for this data set I also made a model, which normally not really used, but I just want to show how we do the evaluation of generated segmentations by comparing them with the known ground truth. Since I have only one data set, I can use it for training, but normally or frequently it's nice to have an independent data set that network is using for validation. And first I will show how we can split the single dataset that we have into multiple datasets. Again, in this particular case I will probably use the full dataset for training, but I just want to illustrate this idea of dataset splitting. So in this window I loaded the training dataset and the corresponding model. Then I can go to the File, Chopped Images Export tool of MIB. And this tool allows me to split the dataset in multiple undefined number of blocks. For example, now with default settings, it will chop the dataset into two subblocks. That would be the block number 1, and that would be block number 2. If I put number 2 here, then it will split it into 4 blocks. Since the dataset is rather small, I would actually want to have, maybe I'll do the 3 blocks, so it will split dataset like this. So I'll take 2 of these blocks for training and 1 block for validation. Since I'm also interested to have the model with the data, I click here, chop the model. So in this case, the tool will chop together the actual images and the corresponding models. The next step, I defined where I would like to chop it, and my data now, I have my project directory for this project, and this directory, the data is in this 0 preprocessing. I'm creating a new directory for training, and I put there, I select it as the destination. so that the chopped data will go to the training directory. And I will use a mirror mesh format for images and the model format for models. And just to chop the data, I press the chop the dataset button. If we check the training directory, we can see that now we have 3 datasets, and they are encoded as the original file name and then indices of the corresponding blocks. So you can see that this is x1, x2, x3, which means that this x2 is actually the middle slice from the dataset. We can load this, and we can see that's the middle slice. And also we have a corresponding model, not this one, but this one. The result of this chopping that we got 3 datasets which are quite narrow, and we would like to use 2 of these for training and 1 of them for validation. Also, we need to create another directory, and there we will use datasets that we would like to predict when the training is done. And in this case, this is the prediction dataset, and I also put there the model, so that I can evaluate the performance of my network. The tool is located in the menu Tools, Deep Learning Segmentation. The first thing when we start the project, we need to define, we need to define the project architecture. Now I would like to do 3D unit, so I select it. Speaking of units, so in the previous tutorial I showed the schematics of UNet, where idea is that the input image is filtered with multiple filters, convolutional filters, and then it is downsampled twice. Then again it's filtered with number of filters and downsampled twice. And this procedure repeated as many times as we want. When it reaches the bottom, after that there is the upscaling part, when the datasets are actually upscaled twice at each of these iterations. And at each moment the filters, the features, are actually combined from the downsample and upsample passes. This is the 2D, and in 3D the difference is that it's the filters, these convolutional filters, take place in 3D space, and these max pooling operations, when we downsample or upsample datasets, take place also in 3D. You can check the corresponding paper. So this is the corresponding paper about use of 3D units, and I'll put the reference in the description as well. We defined the architecture, and now we need to set the directories. So what I can see here, that the directories are already kind of specified, but let's go again through this. So we select the first directory, which would be training. Then, and in this directory we have images for training and validation. Then there's the second directory with the images for prediction. In my project it's 2 prediction. And the final directory we need to specify for results. I normally name with 3 results. So this naming with letters just make them in this kind of pipeline sequence, and it's clear that I go from this step to this step to this step, and then finally to results. The file extension allows us to select the standard extensions such as a mirror mesh, JPEGs, MOV, MP4, and so on, or we can use this bioformats reader. In this case we really can open any of these microscopy formats. We need to specify this extension for images, which is in our case a mirror mesh, and the models stay in MIB model format. Since in both cases I have a mirror mesh, I keep this as AM. We can compress the images as I explained before. Now we can also specify the fraction of images that go to validation. Since we have 3 datasets and we want 1 of them for validation, so our fraction is 0.33. The new thing which was added here is this random generator seed. When the images are split into validation and training, it's a random process. But to control it, we can put index of the seed, which will be used to initialize this random seed generator. Now it's 0. If I process the images, then they will be split into these training images, training labels, validation images, validation labels directories under the results directory. And our training directory has now the first block and the second block, x1, x2, and the validation is x3. So the third block is used for validation. If we change this number, let's say to 2, then the randomization will be different. And in this case, the training images becomes, for example, as first one and the third one, and the validation is number 2. So you can use this if you, for example, the sorting works not the way you want. Let's say you have 2 data sets, one for training, one for validation, not S3 as I have now. And you want to make sure that the one which you defined for training will actually go into this training images and training labels directory. To tweak this, you may change this random generator seed. Let's return back to 0 and do the preprocessing. Right. In addition, we created this prediction images directory where we will keep the results of the prediction, but for now it's quite empty. I'm sorry, it's not empty because we actually pre-processed images for prediction, since we placed the dataset in the prediction directory. So this dataset was converted to this MATLAB format, and the corresponding ground truth model was placed into this ground truth labels directory. Now we're going to the second tab, which is the actual training. And in this case, what we need to do, we need to specify the settings. And as I see from here, they look pretty much the way they should be. So our data set has 70 sections. So technically what we can do, we can try to put 70 by 70, the size of our input page size. And the fourth number here is number of color channels. And our data set has 2, so I need to put 2 here. The explanation of the sequence of this number is actually, you can see in this tooltip. So it defines height, width, depth, and colors, the number of colors in the input page size. Then we need to define what would be the padding. So the padding defines whether the images, when they travel through the network, whether they will be smaller at each of the steps. As you can see, the first convolutional padding, we started with 572 by 572, and after the first step they become 2 pixels smaller. I was explaining this in the previous video, and this manner, the standard way how it was done in the unit, is defined with the valid padding. If you keep the same, then the images will stay as 572 all the way up to here, and then it will be twice and stay kind of twice smaller during all of these steps. There are certain pros and cons in each of the cases, but for now the valid normally gives better results, but it's more sensitive to the parameters which we specify here. The next thing is define how many classes we have. So if we return back to our data set, we can see that we have 3 materials, but the classes in DeepMIB assumes that the exterior is also our class. So what we need to define, we put 4 here, since we have exterior, which is zeros, then we have our cells, nuclei, and synapses. So we have technically 4 materials. The next thing is define number of levels in the network. So 1, 2, 3, 4, or 3, and then this is just depends on what's the size of the input page size. We can keep now 3. The next thing, define how many pages per image we will take. So the dataset is quite small, so I can leave it 32. I can make it even smaller. And then we can also define the mini page size. For now, we just keep them as they are. Number of filters, how many convolutional filters are done at each step. I have quite small image, I can make it bigger. And the filter size. Let's check our network. So the tool says that because of this configuration, it can't really make it 70 by 70 by 70, but it suggests that we can use 92 and 92, 92. which is nice, but we can't do that because we just have only 70 sections in the full stack. So we need to find another parameter. There are two options here. So for example, we can change this to the same and check it again. In this case, it says, okay, 72, 72, 72 should be, which is quite close already. Maybe if I change it to 68, 68, 68, and try now, it will tell me, okay, that I need to have actually 64 by 64 by 64. At the same time, let's see, if I put 64 here, actually, let's see, check network, the difference. So now reminds that we're at the compiled version. And the difference is that the compiled version doesn't have this nice MATLAB tool that shows the network. So we limit it a little bit to this kind of more simplistic preview. So we can see here, we can see the configuration of a network with all the layers. We start from here with the image input layer, go through this 90-degree rotated U shape, and then we ending up in the final segmentation layer here. If you're using Windows version, you'll see also the list of layers in this in the command prompt here. But the most important parameters perhaps are here, which we can see the input page size, which is the one we defined. But it's important to check this output page size. So now we're using the same padding and these are the same. And we have the 4 classes. Now let's take a look on the valid. I'll close this. Let's check the network. So it says that, okay, it won't actually have 92 by 92 by 92. Let's take a look what would be the closest configuration that we can actually afford in this particular configuration. Okay, let's put so apparently with these settings you can't really get a very nice configuration. But let me show you one still effect. I will put this 92 as it suggests. So the important part here, okay, it suggested that it can actually make this network. But the problem is that we need to take a look more carefully is this output page size. Now it is 4 by 4 by 4. It means that when we go through this network, our resulting block that will be predicted will be just this 4 by 4 by 4 pixels. It means that this network is totally inefficient in the segmenting the volumes. Basically, the reason for that is that we have too many layers. We have 3 layers now. And well, we can fix it if we put, for example, encoder depth to 2. Let's take a look now on the network. You can see here that the network became not as deep. So we have like 1, 2 layers, and then 2 layers on the way back. And now with the 92 by 92 by 2 by 92 pixels input page, we actually will generate it once 52 by 52 by 52 pixels, which is the way better. It's still kind of the final block is still small, but this is at least affordable. Okay, but can we do it for our network? Because we have 70. Let's try this 68, 68, 68. Yes, we can have a network with the valid padding with the 68 by 68 by 68 input page size, and the output page size would be about 30 pixels. Again, not totally optimal, but it's okay. And again, the other solution is to use same. Would be the segmentation would be slightly not as nice, but at least it will allow us to get the same output page size as the input page size. Check also input layer settings. Again, the default parameters work quite well in this case. If they won't work, then you can change it to something else with your data. We can tweak the training settings. Maybe for now let's put like 20 epochs, or maybe 50 epochs, because I think they should be quite quick for this data set. We can put validation to, let's say, 100 iterations and keep the other settings as they are. We can change also the final segmentation layer, but again, the dice pixel custom classification works quite good because in this case we have the small synapses that are in one part of the data set. They're not here. So there could be a situation when the patch that we provide to the network won't actually have those. And in these situations, this dice pixel custom classification layer is the way better. We can check the augmentation setting, and then here I guess these are the available tools or ways how the data is augmented. They're quite basic, but what we can define the fraction of images that will be tweaked using these tools. Maybe we keep this as 80%. We can save the progress after each epoch, and we can also export the training plots for later evaluation. Now to start, we press the train button. We confirm that we processed the images. We did, so we press yes here, and then we start training. Now comes the second difference with the MATLAB version. In MATLAB version, if you again have seen the previous tutorial, you can see that there is a nice plots that you can follow the training. And in this case, this tool is not available in the compiled version, so I have to rewrite this window. It's slightly different, but it shows basically the same things. So in the upper plot, we can see the accuracy, and in the lower, we can see the loss function. What we try to do, we try to minimize this function as low as possible, or perhaps not we, but the network. Here we can see the training times, we can see how long we already been training, and how much time it would still require us to go, which is actually missing in the MATLAB version, and in this sense I really even like this window more. Additional information about the training cycle can be seen in this training cycle fields. So we have the iterations, we have 16 iterations per epoch, about 800 iterations will be altogether, and then the validation frequency is 100. So after each 100 iterations, the network will be checked, is going to check itself over these validation datasets that we provided. This plot takes some resources to draw, and what is possible to do in the training settings. So I pressed here on the training settings. What we can do, we can switch the plots to none, and in this case this window won't be shown, and the whole progress will be displayed in this in the comment window, but you can actually speed up the process in certain way without drawing this window. For now, I'll just pause a little bit the video and wait until the training is done. Now the network is finished, and we can follow the progress of that training. We can stop the training at any time by pressing the stop button, but it is recommended or actually you have to wait a little bit. There's another dialog which is running, so you need to wait until that dialog disappears. So we've done the training, and as a result of the process, we've got, what I forgot to say is that we need to specify directory where actually we want to put the network. So this is kind of rather important. Now we put into the default place, which was initialized when I opened the DeepMIB, and it matches the same as the directory which I had in MIB. What I can do, I can go there. So, and what I've got two files: the config file and the actual network files. As I was explaining before, the config file has all the settings, but it doesn't have actual network file. On the other hand, this DeepMIB has the network and the settings, but it's missing the directories. So it's kind of a lighter version of this one. What I can do, I can move these files into my project directories here. And now let's try. So the problem really that these files, how they were stored. So let's take a look. I will go and load the project and then double check that whether I have correctly this these parameters, so I need to specify this directory again. And that seems to be correct. If I'm not sure, I can always go and load the network itself. So I can go to the next tab, which is predict, and here select the network file, and this network file will be used for prediction. We processed the images for prediction already. If we haven't done that, or for example we'd like to use the tool only for prediction, then we have to return back to the directories and preprocessing tab, select the directory for prediction, choose preprocess for prediction, and press the preprocess button. Okay, so we have these images now that we'd like to predict. Now I'm switching back to the predict tab and press the predict button. Double check the question whether we preprocessed the images. We did, and the prediction is starting. So there is a timer that shows how long we need to wait before the prediction will be finished. The dataset now predicted, and that progress bar got closed. The result of this operation is that in the results directory under prediction images we have a directory with models. So this is the model that corresponds to the prediction dataset, and directory with scores. We can open those. The easiest way is just to press this load models. When I press this, MIB loads the dataset that we prepared for prediction and loads the model that was generated during this training process. So what we can see here, we can see quite nice segmentation of the cells, their nuclei and synapses. If there are certain problems, those could be a little bit like filtered manually or semi-automatically. For example, with this around this nuclei, there could be still some possible issues. We can also check the scores. So if I press this load prediction scores, it will load the file where we have 4 color channels, which matches number of materials that we have in the model, including exterior. So the first channel shows the probability for the first material, which is exterior in our case. The second is cells. The third one, nuclei, and the fourth one, synapses. By turning on the multiple channels, we can see the basic probability of having one or another material in the final segmentation. We can also evaluate segmentation. Since we had the ground truth model next to the prediction dataset, we can do evaluation. So with this, we can select the metrics. The tool tries to compare the dataset that we provided with the ground truth with the one that the network generated. We can see this confusion matrix, which basically means that the true class synapses so was identified with this 89% correct prediction. So you can basically see how well the network performed. We can also save these images or save these values into a file, Excel file, or export to MATLAB. And also you can see here the actual results, the Jaccard metric for each of the classes. So if I press the OK button, then in the results, prediction images, models, I'll get these 2 files, evaluation results, that have all kinds of metrics that we selected. So I started evaluation results Excel file, and this Excel file has several sheets which are named. So this is the class metrics. So these are like 4 classes. Unfortunately, the column here can't be saved. So what I can do, I can get from this confusion matrix, I can take this matrix, shift it by 1, and then populate this field with the names of the materials. So this is the confusion matrix, and the same we can do for class matrix. I can just move it here, and then instead of this field I can copy the actual materials that I have. So we can see the accuracy, intersection, and intersection over union. And the same metrics could be available for each images if you have multiple images. Also, we can explore activations. So this is the mechanism how you can see what is going on inside the network. What we have here, this is the image. So we have only one image now, one data set, but otherwise I can select multiple. Then we can select the which layer of network we'd like to explore. So we start with the input image layer. This is the patch that is directed to network. So what we can do, we can change its Z, and we can shift it. Let's say put it 150, 50, like next to the nucleus. Maybe go a little bit deeper. Okay, then I press update here, and I can see this area. So this is the channel 1, which we send to network, which is like the red channel. And we can see the channel 2, which is the nuclei and synapses. And then after that we can go deeper. For example, let's say this encoder stage 1 ReLO 2 layer, and then it shows us the various filters that were acquired at that stage. And we can see the actual image, and we can see what are the image intensities to see the highest, for example, signal that was generated. At the end of the network, we can check this, for example, final convolution layer. You see it's way smaller. So this was our original dataset, and this is the predicted area. And we can see the predictions for different classes. So this is class 1, which should be perhaps exterior. Then class 2, 3 should be nuclei, and the 4 should be as far as I remember, synapses. But again, this is our window, so the synapses didn't get there. What we can do, we can check, let's say, move it by, make it more towards the center, and press update. And here you can see that the probability that this pixel is actually one of the synapses is pretty high. Alright, finally, in the final tab, you can see here there is the load and save config. So what happens also in the config, by default config saves the location of these directories relative to the location of the network. So in this sense it's very nice, so you can move the network everywhere. But it doesn't really work in the situations when your network file is kind of inside one of these. So it should be in this kind of the network file should be, let's say, in my project. It can't be inside this one training to prediction and 3 results directory. Okay, so with this I'm finishing now. Thank you for your attention, and if you have any questions you can always refer to the help section, which is open by pressing this help button. Thank you very much.